Welcome to Unit 5 of Reservoir Geomechanics. In this unit, we're going to be talking about the composition of reservoir rocks, their fabric, their elastic properties, and the anisotropy of elastic properties. And so first, we'll focus on actually what these rocks are made of, what they're composed of in terms of the different mineral constituents, and how those mineral constituents are arranged to form a fabric that gives rise to anisotropy. We'll focus on static and dynamic elastic properties, mostly focusing on lab measurements made on core samples. And then we'll spend a little bit of time talking about theoretical bounds on elastic properties, figuring out how we can use simple models from rock physics to better understand both the anisotropy as well as the variations as a function of composition. Then we'll spend a short time talking about pore elasticity, what sort of coupling occurs when there's fluids in the rock and it's subjected to stresses. And finally, we'll end up talking about estimating elastic properties from geophysical data and try and integrate observations from the lab, well logs, and unconventional reservoirs. So in this first section, we'll focus mostly on the rock frame. And the first thing to talk about is sort of how we classify these shale reservoir rocks. So there's two main ways we can actually use to classify these rocks. On the left is a ternary diagram in the space of clays, silicates, and carbonates, which shows rocks from many of the major U.S. shale gas reservoirs. You can see that there's a broad range of compositions actually represented here, and samples from different ages, reservoirs of different ages, actually plot in a wide range of compositional space. So what this tells us is we need to adapt some compositional metrics to try and actually classify these rocks so we can learn about their mechanical properties. On the right is a classification based on grain size. And so on the top we have sands, so sand size grains that are greater than 62 microns. On the left, clay grains that are less than 2 microns. And on the right is silt grains, which are intermediate between those sizes. And so really when we're talking about these reservoir rocks, we're really talking about things in this area of the triangle. These rocks are significantly fine-grained, and because of that, we would consider basically all of them to be either mudstones or claystones just based on their grain size. Now, if we return to the plot on the left, we can actually draw some distinctions about the different compositional groups here. And this is a fairly detailed classification, but helps us to some degree understand the different types of reservoir rocks. So in this bottom right corner, we have extremely carbonate-rich samples, which we might call, again, calcareous because of their composition and mudstones because of their fine grain size. And that transitions all the way to the left side of the plot where we have more siliceous mudstones and to the top of the plot where we have argillaceous or clay-rich mudstones. So this is an important classification to keep in mind when we start talking about the mechanical properties of these rocks. The space that we'll look at most commonly in terms of these ternary diagrams will be something that's specifically adapted to these shale reservoir rocks. And this is a ternary classification based on clay plus organic matter, the softest, most compliant components of the rock, carbonates, and silicates, including feldspar and also pyrite, which is very common in these rocks. So here we have rocks plotted from various U.S. shale gas reservoirs again, and we're plotting both vertical and horizontal samples. Vertical samples being those where bedding is perpendicular to the core axis, and horizontal samples being those where bedding is parallel to the core axis. So we'll keep that convention moving forward. And one thing that I want to point out is that the compositional variations in these reservoirs are actually occur on a very fine scale. And I'll give you an example of that. Here's a rock from the Barnett Reservoir at a depth of 2616 meters. This is the sort of core sample that we'll be focusing on in terms of the laboratory measurements that we'll discuss later in this lecture. But you can see that this is a very light-colored sample. It plots to the bottom right of the plot, meaning it's very poor in clay and organic content and very rich in carbonate. Over here is a rock from basically 2 meters away from the same exact Barnett Reservoir, and it has almost 50% difference in composition. It's significantly more siliceous. It's still quite clay poor, but the composition differs quite a bit just 2 meters away. And even another about 10 meters away, we run into this extremely clay-rich sample. And visually, you can see that all these samples are very much different. But again, they're within several meters of each other. So this emphasizes the fact that you can get these very large-scale compositional differences happening in very small spatial scales inside these reservoirs. The next thing we need to talk about is the actual matrix components that make up the rocks. So we already discussed clay minerals. They tend to be mechanically weak and chemically reactive. Because of their inherent intrinsic porosity, they're subject to increased compaction and plastic flow. Again, we discussed that the grain size, or really the particle size of clays, is everything under 2 microns. And we'll look at that in a little bit more detail in a couple slides. But one really important thing about clay minerals that is going to impart part of the properties of these shale reservoir rocks is they're inherently anisotropic. And what I mean by that is that their crystal structure actually causes variations in mechanical properties in different directions. And again, we'll look a little bit closer at clay's crystal structures in order to drive that point home. The other aspect of clays is they are often authigenic, which means they grow in situ, which means that a lot of the clays we see now in these reservoir rocks actually developed during the heating and burial process during which the rocks were formed. The last component that's important, and this is directly related to the inherent anisotropy of clays, is they often have anisotropic porosity associated with them. And again, when we start looking at some microstructures of the rocks, we'll focus a bit more on that. The next group to talk about is carbonates, phosphates, and oxides. And these components of the rock, in contrast to clay, are mechanically strong, but also chemically reactive. This means that in rocks with high carbonate, we can expect increased dissolution or precipitation as a result of interaction with slightly acidic fluids or CO2-bearing fluids. Again, the grain size of these components is much larger than clays, about a order of magnitude. And we mostly find silt to sand size grains of carbonates, phosphates, and oxides. And these are sometimes distributed as fossils, sometimes distributed as veins, and sometimes distributed as mineral cement surrounding other grains in the rock. The last component in this diagram that we need to discuss is the silicates, quartz, feldspar, and pyrite. And these components are mechanically strong, but actually chemically stable. They tend not to react with fluids or other components of the rock. And again, these are much larger grains, again, silt to sand size grains. And one important thing about quartz is that based on the temperatures of these reservoirs, the quartz has actually gone from the opal CT to quartz transition. And the significance of this is this transition actually produces microcrystalline quartz in addition to what happens when clays actually change from smectite to illite. And we'll focus a little bit on that later when we talk in more detail about clays. So when we think about the clay content of these rocks, we're really talking about rocks about 0 to 60 weight percent in clay. And on the right is a collection of rocks from the same reservoirs that we looked at in the ternary diagrams, showing the distribution of total organic content versus clay content. And what we can see is that there's quite a bit of scatter, but in general, clay content seems to be positively correlated with total organic content. Each of these lines that are drawn on the plot are actually fits to the individual reservoir data. So you can see that the trend for different reservoirs is quite different. And that obviously is owing to the different depositional setting, burial, and maturation history that they all have experienced. But in each one, there's an approximately positive correlation between clay and total organic content. And in the future, when we talk about elastic properties, we'll actually come back to that as a useful tool for actually creating some simple models to describe the properties of these rocks. The clay mineralogy that we're talking about, the types of clays, are mostly illite and illite smectite interlayers. There's sometimes small amounts of kaolinite and chlorite, but for the most part, we're talking about illite and illite smectite interlayers. Now, if we look at what these different clays actually are, on the left is a representation of the atomic structure of smectite and illite clay. And one thing that you can see right away is both of the clays are composed of alternating tetrahedral, octahedral, and tetrahedral layers. And each of these layers is part of the fundamental unit of a single clay grain. And so when we talk about the clay particles, as we can see in the scanning electron microscope image on the right from the Haynesville Shale, it's a very clay-rich sample from the Haynesville Shale, the scale on the right over here is 250 microns. So each of these small particles that we're representing atomically on the left is actually a very small component of each of these particles we see on the right. So it's important to consider that although visually we can see that clays form these bedding parallel aggregates, those aggregates are actually composed of many, many, many clay grains or fundamental atomic units of clay. And so if we come back to the left, we can see that the big difference between smectite clay and illite clay is actually coming from the interlayer. Expandable smectite clays are expandable because they have an interlayer that can range from about 1 to 10 microns, depending on the type of cations and the presence of fluid. And in fact, when smectite clays interact with fluid, they can actually integrate water into their interlayer and expand quite a bit. A component of the illite clay is that it actually has strong cations inside the interlayer, and because of that, it's not able to expand during interactions with fluid. And again, the fundamental particle size, 2 microns, this represents a very small component of what we actually see microscopically in these rocks in terms of the particle size, which is represented in the scanning electron image on the right. So if we go to the image on the right for a second, we can see maybe 2 properties of the rocks that which you talked about before. Again, the atomic images on the left show us that the rocks are, the clay minerals are inherently anisotropic, meaning that if we travel in different directions in the crystal structure, we actually see different chains of atoms, which are going to give us different physical properties. We can see that actually scales up on the right because the particles that are made up of these inherently anisotropic minerals are also shape preferred. They're elongated inside the bedding plane. And this means 2 things. One, that the particles themselves are anisotropic, and 2, that the porosity associated with these particles, you can see these small pores and spaces here, those pores are also anisotropic in themselves. They're elongated in the direction of bedding. One thing I should note that is when we look at most of these microscopic and petrographic images of rocks, we're always going to be looking with the bedding plane horizontal because this is an approximately in-earth, in-situ view. So that's something to note going forward. Clay mineralogy is important to consider because in the Earth, there's a strong transition at fairly low temperature from expandable smectite clays to non-expandable illite clays. And because of that, what we often see are these illite-smectite interlayer structures, which can be mixes between both illite and smectite clays. And this mixing can either be random, it can be regular, or it can be segregated, where there's in fact different blocks of pure illite and pure smectite clays. But this interlayer, because of the presence of smectite and because of its different interlayer structure, whether random, regular, or segregated, can actually expand up to 25% in volume due to adsorption of fluids or gases. So this is an important quality to consider when looking at the clay mineralogy of any reservoir rock. Now, the smectite to illite transition can be seen on the plot to the right. And so this is some data from Gulf of Mexico shales from Ho et al. And what they're basically showing here is a depth section in which the gray points represent the percentage of illite in the rock. And you can see that in the shallow part of the crust, about 0 to 2 kilometers, there's not really a huge change in the percentage of illite in the rock. When we get to about 2 kilometers, which corresponds to the range of about 70 to 100 degrees C, we actually get a very strong transition in the mineralogy where a lot of the illite or a lot of the smectite in the illite-smectite interlayers gets converted to illite. So we can see right here at 2 kilometers, there's a strong transition in mineralogy, and then we almost have a rock that's pure illite in terms of what's in the illite-smectite interlayers at significant depth. The other aspect of this plot that's important is actually the fabric of the rock. So this means that how well aligned are these clay particles in the structure. And as we're going to see later in the lecture, this actually is extremely important for the anisotropy of the rock. And so what we can see is that if we look at just these black triangles here, the illite fabric is, again, fairly constant until we get to that about 2 kilometers where this illite-smectite transition is occurring. And then we see a big jump in the fabric. That results from 2 things. One is that there's actually authigenic growth of illite during that transition. So that means illite is growing in place under the stress of burial, which often creates growth in that bedding parallel direction, and thus further enhances any existing fabric. The other aspect of this that's important, of course, is that this transition will actually generate interparticle microcrystalline quartz. And that quartz might be important actually for supporting these clay layers and actually adding some strength and reducing the porosity of the rock during burial. So now that we mentioned a little bit about the clay fabrics, let's look overall at the crystal fabrics inside of shale. So this is some work that's X-ray goniometry work, which is using X-rays to actually identify both the mineral phases and how well those minerals are crystallographically oriented inside the rock. So here are 2 examples on the left from the Benken Shale and on the right from the Posidonia Shale. And in both plots, you can see kind of a similar trend. On the left, you see that the minerals that are aligned, the minerals that have a strong preferred orientation, that's quantified by this multiples of a random distribution. When the multiples of a random distribution is close to 0, it means that you're near a random fabric in which the grains are oriented in many different directions. And the higher that number goes, the closer you have to a single crystal fabric in which you have a single preferred orientation for the minerals. And so what you see in both plots are the clay and phyllosilicate minerals are the ones that have a strong preferred alignment: kaolinite, illite, and chlorite. Whereas quartz and calcite, for example, are very poorly aligned and are not particularly contributing to the rock fabric at all. So this kind of gives us a hint at where the anisotropy of these rocks is starting to come from. On the right, we can see rocks S1 to S4, and these rocks are varying in terms of their thermal maturation. So this factor R0 here tells you about the degree of thermal maturation of the rock, which says something a little bit about the maximum temperature of burial and the state of organic matter in the rock. What's important about this is that we can see that throughout these different maturities, there's a pretty consistent orientation as far as the clay minerals are concerned. So we can see that in this case, the act of maturation doesn't actually create any additional clay fabric. The next component that we'll talk about are carbonates. And so carbonates can be an extremely important characteristic of these shale reservoir rocks. In fact, we see carbonate contents up to about 90% in some of these reservoirs, which essentially make them limestones. But again, because of their fine grain size, we would classify them more as calcareous mudstones. And so these plots here show, again, the same set of samples we've been looking at in terms of the pyrite composition and the total organic composition. And each of these have actually a similar trend in terms of carbonate content. And if we think about the deposition of these rocks in oceans or shallow seas, what we see here is that actually the conditions under which you get high total organic content and the conditions under which you get high pyrite are actually sort of the same. So when we see situations in which we have anoxic burial conditions, this means deep water depositional conditions below which the water is so anoxic that you can actually preserve organic matter. It won't be oxidized. And also you have enough bacterial activity to actually turn sulfate from the seawater into sulfide, which helps you form pyrite with any iron that's present. And so the conditions for high pyrite and high TOC tend to correlate, and we tend to see those, again, at low carbonate content. The next thing to talk about is organic matter in the rock. And so organic matter is extremely important for these shale reservoir rocks because, of course, the rocks themselves are both source rocks and reservoir rocks. That means the organic maturation, creating hydrocarbons, actually happens in place. And so organic matter ranges from about 0 to 20% in terms of the weight percent of the rock. But because it's about a factor of 2 less dense than all the other mineral components, it actually ends up being about 0 to 40 volume percent when we think about it in those terms. Again, we saw that organic matter is positively correlated with clay content. And one thing that we can see if we investigate rocks using a scanning electron microscope, again, these are 4 images taken from different shales, again, where bedding is horizontal in each of the images. We can see that organic matter presents itself in various different morphologies. So in the top right, for example, we have large lenses here that are elongated in the bedding direction. Over here, we have actually a coccolith fossil with a calcite shell and both clays and kerogen inside. And on the bottom over here, we have 2 different examples of microfractures in the rock, again, which are oriented parallel to bedding, but filled with organic matter. If you look closely, also in each of these images, you see some more isolated deposits of organic matter that are throughout each of these rock structures. And again, it's important to note the scale over here. We're talking about scales now in the tens of hundreds of microns in terms of the distribution and size of these features. And of course, the differences in each of these rocks are going to depend strongly on a variety of factors. The source material for the organic matter, what sort of biological organisms have been deposited with the rock and are giving rise to the organic content. The depositional history, how fast, how hot, how deep has it been buried? And also, finally, the mobility of organic matter when in the rock matrix. For example, when the rock starts to mature, what happens to that organic matter? Does it escape and move to another sort of reservoir in the rock, or does it stay in place? Again, a lot of that is going to depend on both the permeability and porosity as well as the specific depositional history. And that's something we'll touch on a little bit more in a later lecture. The final component of the rock we need to talk about is actually the empty space inside the rock, the porosity. And so porosity in these extremely low permeability unconventional shales ranges from about 0 to 10 to 15% at most. And again, we see that because clays and organic matter actually contain a lot of the porosity in the rock, it's not surprising that in each of these reservoirs, although the trends are different, we have a slight positive correlation of porosity with both clay and organic content. And again, if we go back, we can see that the distribution of these things, these organic deposits throughout the rock, as well as the distribution of clay, because these components are correlated with porosity, we can expect that porosity might be distributed within each of these components as well. Now, when we talk about pores in the rock, there's a whole ecosystem of different sorts of pores. So if we just consider, again, a ternary diagram like we have been, except this time the axes are actually pores in organic matter, pores that are interparticle, pores between different particles, and pores that are intraparticle, pores within certain particles. Using this classification, we can see a range of different things in the rock. First, the pores between or within particles can be simply pores within grains. They can be pores within crystals or pores within clay platelets, as we saw before from that example from the Haynesville Shale. We can also have intraparticle pores, meaning pores inside those clay platelets that actually are pores between those individual clay grains. We can have pores inside, for example, pyrite, or dissolution rims with inside calcite or fossil bodies. So there's a range of these pores that can happen either between or within mineral particles. Then a whole other classification is actually pores within the organic matter. And this will be an extremely important source of porosity in these rocks. As we see, porosity is correlated with total organic content in most of these reservoirs. And that's to be expected because actually during the maturation process, the heating and burial of organic matter is actually going to allow hydrocarbons to escape from that original organic material, leaving behind a porous structure. The last class of pores, which we saw briefly in the previous slide, for example, here are microfractures, which can sit inside the mineral structure and are mostly, you find them mostly parallel to the bedding plane because that tends to be a weak plane over which the rock can actually part and form fractures. So that now that we've understood the range of different pore sizes and the range of different pore types and the mineral components of the rock, let's start looking at some of the rock structures in detail. So to do that, it's useful to classify rocks on individual compositional trends. So for example, these three images here, which are plain polarized light petrographic images, show clay-rich shales from the Barnett and Haynesville reservoirs. And in these images, clay content is increasing from left to right. And so what we see is that several things happen when you start to increase the clay content of the rock. If we just compare the left and the right images, what we see is actually that both the grain size and the grain shape are changing. The grain size is, of course, decreasing because we're moving from larger particles of calcite and quartz to smaller particles of clay that are inside the matrix. The grain shape is decreasing because, again, we're moving from these equant to circular grains of quartz and calcite to, again, these layered structures of clays, as we saw, again, in that example from the Haynesville. The other thing that's happening as we increase the clay content is we're increasing the fabric strength or anisotropy of the rock. And you can see that just by looking at these structures in detail. As you look left to right, you can see that on the right, more and more of the components of the rock, particularly the matrix itself, seem to be aligned inside the bedding plane, aligned, elongated parallel to the bedding plane. And this is going to be, again, a major source of anisotropy in these rocks. When we talk about the anisotropy, it's important to distinguish three different sources that are not exactly independent, but somewhat linked. Again, the intrinsic anisotropy refers to the anisotropy of the clay grain itself, the actual mineral structure. The grain shape, or in this case, the particle shape, these elongated platelets that result from many, many clay minerals being put together in these aggregates, that again is another source of anisotropy. And again, finally, the pores that result from those aggregates being stacked on top of each other in somewhat of a misaligned fashion results in elongated pore shapes that again contribute to the anisotropy. So three sources of anisotropy as you increase the clay content of the rock. Now, if we look at another compositional trend that's common in these rocks, we can look at the trend of increasing carbonate content. So here, these are examples from the Eagleford and Barnett shales in which carbonate content is increasing from left to right. And this is a significantly more complicated compositional trend because for one, carbonates can range from maybe 0 to 90% in these rocks, mostly comprised of calcite and dolomite. So it's a quite wide compositional range. But increasing carbonate content doesn't necessarily mean that either fabric will increase or decrease. It doesn't necessarily mean that grain size or grain shape will change in any sort of a regular way. And this is because the carbonates in these rocks mostly come from biogenic sources. And so on the left here, you can see that actually the carbonates in this rock are composed mostly of these little coccolith grains, which are small marine fossils. And those are distributed among clay and quartz in the matrix and small deposits of kerogen. In the middle, we can actually see a structure where we have much less of those coccoliths, but this sample is actually higher in carbonate because there's fine-grained carbonates inside the matrix. And again, the processes of burial and maturation can result in huge microstructural differences between rocks with similar composition, because the processes of dissolution and reprecipitation of the carbonates can actually move those initial biogenic structures, move the carbonate from those initial biogenic structures out to different components of the rock. And you can have mineral fill rather than intact fossil grains, as you see on the left. On the right, this is a barnett sample with extremely high carbonate content. And you can see that rather than discrete biogenic grains, we have sort of a coarse-grained matrix that's extremely cemented together and large calcite grains that are very different from what you see in either of the two Eagleford samples. Again, as we look left to right, unlike the clay minerals, there's no sort of regular evolution of both anisotropy as well as grain size and grain shape. Again, because the sources of these carbonates can be quite different, between different reservoirs, and even within individual reservoirs like the Eagleford, differences in the processes of burial and either dissolution or reprecipitation can create big differences in the mineral structures. Another point that's important to consider, and we looked at it actually briefly in terms of heterogeneity inside the reservoirs on the scale of meters or tens of meters, is the fact that even within these core samples, so on the left is a vertical image of the face of a laboratory core sample that we'll be talking about elastic properties from later, you can see that, and again, this is what we call a horizontal sample, because the core axis, which is now in and out of the page, is parallel to the bedding plane, which again is horizontal in this image. But if we just look at this rock as sort of a microcosm of the reservoir, we can see that if we pick just 4 random regions across the rock, that the rock itself is actually composed of these microfacies. It's actually layered on a scale at about the centimeter scale and below. So, for example, in area 1 here, we see these bedding parallel streaks of organic matter among a fairly clay-rich matrix with about equant grains of quartz and calcite sitting around. In area 2, we see very little organic matter, and instead of being distributed in large veins, it's actually in these much smaller lenses that are within the matrix. In area 3, we have, again, smaller lenses and isolated deposits of organic matter, but the rock matrix is mostly composed of these sand to silt-sized grains of quartz. And in area 4, we have a very similar texture, but with even more quartz and less of the clay-rich matrix at this time. So you can see that even within the scale of centimeters or below, it's possible to have strong heterogeneity of both composition and also microstructure within these rocks. So in the next section, when we start to talk about laboratory measurements, it's important to understand that each of these laboratory core samples is actually an integrated response of many, many different compositional groups inside the same rock. And this is something that we'll dig into a little bit in a further unit where we focus directly on the microstructure and pore networks of these rocks.